the regression process, let's have a look at an illustration. Suppose we want to know what the relationship is between corporate sales and GDP growth. In this illustration, therefore, corporate sales would be the dependent variable and GDP growth would be the independent variable. In other words, GDP growth determines what happens to corporate sales. And that kind of makes sense, right? So if the economy is expanding, corporate sales generally go up. Now, to estimate what the relationship is between corporate sales and GDP growth, what we're going to do is we're going to look at some historical data from a sample period. And let's just suppose we're looking at monthly data over the last 5 years. So that constitutes 60 observations. And then what we're going to do is we're going to take those observations and then we're going to regress the sales data on the GDP data. Now, another word I like to substitute for regress is relationship. So when you see regression, what it's really saying is, what is the relationship between sales and GDP? So here we go. We're going to do visual depiction of this exercise. We're going to plot sales on the vertical axis and corporate, or I should say GDP on the horizontal axis. And each red dot represents an actual observation from that 5-year period. So let's just look at this dot. That dot tells us what sales and GDP were for a particular month. So for example, in this particular month, corporate sales was over here and GDP growth was over there. So by plotting enough of these points, what we're able to do is we're able to see the general relationship between sales and GDP. And that's what a regression is. It's the line that best fits through all those observations. So that gives us an estimate with respect to what the relationship is between these two variables. Now, formalizing this in an algebraic form, here's what we get right there. So first of all, when you see a hat, it indicates that this is an estimate. And that makes sense, right? Because this regression equation was based on a sample. So it's just an estimate. Because the fact is, we don't know what the true relationship is between sales and GDP. And I'll make an illustration. If I told you what GDP was going to be for next year, can you tell me with certainty what sales would be? The answer is no. Even if we did know what GDP was next year, we don't know exactly what sales will be. And that's why regression is simply an estimate. So basically, the regression is just the equation of a linear line. So we start with the intercept term, and that's what we got right there. And then we go up a slope, which is measured by B1. So that's your slope coefficient. And then when we get to x, right, that brings us over here. And then you have an error term. So because the regression is just an estimate, the estimate and the actual will always be off. Now have a look at this observation. Some errors are above the regression. Some errors are below the regression. So when you average out these errors or you find their expected value, the average of those errors will be 0. Now be careful, that does not mean the errors are equal to 0. It just means the average of the errors will equal to 0 because, again, specifically, this is a positive error because this error lies above the regression line, whereas this one is a negative error because it lies below the regression line. So there it is, ladies and gentlemen. This is what a regression equation looks like. Now let's suppose we're given some values for these. So instead of the generic y hat, that would be sales because that's a dependent variable. And let's suppose our estimate for the slope is B0 and the estimate for the slope coefficient is 0.6 and there's your GDP. So how do we interpret these data points or these coefficients, if you will? So the coefficient specifically refers to the b. So that would be the intercept term and the slope coefficient. So what does the b0 equal to 2 imply? Well, let's see here. Using this very simple example, when would sales equal to 2 when the other terms disappear? Well, how would the other terms disappear if GDP was equal to 0? And there's your interpretation for b0. So if GDP growth was 0, then sales growth would be 2%. Therefore, B0 represents the effects of all factors other than GDP. Now, we got to be able to understand this from a conceptual point of view. And here it is. Here's the conceptual explanation. The fact is that there's a lot of factors driving corporate sales. We know that, right? The changes in consumer income, demographics, etc. But the only thing that this regression equation has for explanation is GDP. But like I said, we know there's factors other than GDP that drive corporate sales. So where is the effect of those other factors incorporated into the regression? Well, if this part captures the effect of GDP, then this must capture the effect of all other variables on sales. Now let's look at the slope coefficient, which is beta 1. It's equal to 0.6. And how do we read that? So at this point, I'm just going to put B0 out of the mix just so we can concentrate on B1 right there. And here it is. So the 0.6 tells us what the relationship is between sales growth and GDP growth. So for every 1% increase in GDP growth, sales growth will increase by 0.6%. So therefore, the B1 represents the sensitivity of sales due to GDP. Note 2. So when we're analyzing the regression output, so with all regression software, you have the standard output. So it talks about coefficients, talks about errors. Now here's the way we analyze the regression output. So we do it in the following order. The first question we have to ask is the regression model valid? And here's what we mean. If the errors are picking up a pattern, then that would imply that the model is not capturing something important, and therefore it's not valid. Let me elaborate on this. So here's our framework for the regression equation. So I showed this to you before, and I also told you there's an error term. Now it's true, the expected value of the errors is 0. But still, each individual observation will be off from the regression. So coming back to this visual framework, you could see that for each individual observation, there will be an error. Yes, it's true, the average of all the errors is equal to 0, but again, individual observations have errors. But the point I'm trying to make here with this framework is the following. Here's the actual observation for Y. If it's not picked up by the regression, then what is the only other variable or factor that's going to reflect what's happening to Y? And here, let me draw some arrows. And there it is. So any variation in Y that's not captured by the regression will automatically be reflected in the errors. So what does the analyst do? The analyst starts working backwards. We first start looking at the errors. And if we see any funny patterns, we'll say that means the model is not capturing something. So what's the point at even looking at it? Now, some terminology, the X, or these independent variables, are referred to as the deterministic part of the model. And you could see why, because we're trying to use the X here to explain what's happening to Y. Now, these independent variables can be continuous, such as stock returns, or they could be discrete. In other words, they can take on a value of either 0 or 1 if X is a dummy variable. I'll just give you a quick example. So for example, we want to know how stock return might be affected by the fact that the stock might be included in an index or not included in an index. So that index inclusion would be considered as a dummy variable. So if it's included in the index, the dummy variable would take on a value of 1. On the other hand, if the stock is not part of an index, it would take on a value of 0. And that's what we mean by discrete. On the other hand, stock returns, they're continuous. So you can have a stock that earned a return of, let's say, 8.569%. So you could see how those values are continuous. And the error is referred to as the stochastic or random component. And that's exactly what the errors are supposed to do, ladies and gentlemen. They're supposed to be random. They're not supposed to exhibit a pattern, because the pattern is supposed to be captured by the regression. That's the whole point. Now, assuming that the errors are random and therefore it's valid, so the regression is valid, the next question is the regression model significant? So just because the model captured all the essential variables, it doesn't mean that it has a strong predictive power. In fact, ladies and gentlemen, most variables in the financial markets are not predictable, even if you have a well-constructed model. So what do we mean by, is the model significant? What we're asking is, does the model explain a significant portion of the variation in the dependent variable? So I have two scenarios here. So we got this one scenario over here and another scenario there. Let's call this scenario A and let's call this scenario B. Now you can see that it's the same regression because it's the same blue line in both cases. But in the first case, look how well the data points lie around the regression. So it's very tight fit. Whereas in the second scenario, you can see that the data points are spread all over or deviate by quite a distance from the regression equation. So therefore, for scenario A, we can conclude that the relationship is significant because the estimates are pretty close. Remember, the red dot represents actual observation, whereas the blue line represents an estimate. So you could see that the actual and the estimate are pretty close together. Whereas in the second scenario, you could see these huge gaps between the actual and the estimate. So in part B, the conclusion is that the relationship is insignificant because the estimates are far off. And finally, once the model is deemed to be valid and significant, then it may be used in order to make forecasts.